I am your TA for genetics lab if you haven't come to my office hours. And a lot of people have some misconceptions about monohybrid and dihybrid crosses, particularly the dihybrid crosses. So I'm making this video to review the monohybrid cross, which I think most of you get. And then we're going to see how it applies to the dihybrid cross and get rid of some of the silly mistakes that people make while doing dihybrid crosses. And I don't mean this as silly as in you shouldn't make them. Everybody makes them. I mean it in the sense that we can fix it easily, and we should. Okay, so the monohybrid cross. We're going to go over the different generations. So this is the parental generation. Unless otherwise stated, and this is it's very unusual for it to be any other way, they are true breeding, which means that they are homozygous, either homozygous recessive or homozygous dominant, right? So I have it written up here. I'm using a notation that I like because it's very clear. So what you need to remember is that notation doesn't matter. All that matters is like whether the gene's recessive, dominant. So sometimes Derek will write a recessive, so like normally, right? So this is, let me explain my notation, and then I'll explain how it's normally notated, and then how sometimes it gets switched around in the questions you're going to be answering. So you have the H plus gene. So what this is the curly hair gene, because we see that this individual with curly hair has two of them. It's wild type, which means that it's the most common found in nature, and it's dominant. Usually the wild type is dominant, it's not always. Then we have the straight hair gene. So this is the hair gene, and with the straight variation on it, right? And it is recessive, which means in the heterozygote, you won't see it. You won't see that trait. So we have these two true breeding parents. So if you selfed them, right, like they would only, so if you were to like breed them with others of their strain and all their same genetics, they would only ever have offspring that looked like them in all of their generations. Okay, so we're going to create the filial generation. So parental, filial. Filial, it is a Greek word meaning brother. So you'll hear it in Philadelphia, and you'll hear it in fraternity. They are the generations that come after the parents. Okay, so in this cross, we're going to do a really basic cross on this Punnett square over here, right? This parent is going to have its genetics through meiosis, right? And then it only has, since it's true breeding, it only has one gene that it can pass on, right? So H plus, H plus. The same with the straight-haired parent. HS, HS. And so when you do this out, you will get 100% H plus HS individuals, right? So I can fill this all out. It's not necessary because we know what it'll end up being. H plus HS. So 100% of the filial 1 generation is going to have curly hair because it is the dominant, that is the dominant trait, and it will have a heterozygous genotype, H plus HS. And we can tell that the curly haired gene is the dominant one because this guy is a heterozygote, and it has curly hair. It has the H plus trait. Now, to create the filial 2 generation, I got a couple of questions in the email about this. What you have to do is you have to mate the filial 1 generation with itself, which is a little gross because they're brothers. So I'm going to erase this board because I only have one tiny board, and then we'll go on to what the filial, so what a cross between two heterozygotes looks like. So we have the parental generation. It created the filial 1 generation. Now we have two heterozygotes here. So now we're going to see what these two heterozygotes, when mated, create, what proportions of offspring they create in the offspring in the F2 generation. Okay, so if you remember from meiosis, you can't keep doubling the genetic information every time, right? So you have to have it. So 1/2 of the individuals will get a H plus gene from this parent. So 50% of the time, they'll get an H plus from this parent, and 50% of the time, we'll get an HS from the same parent. The same thing happens over here. You have half the individuals getting the wild type from the second parent, and you have half the individuals getting the recessive from this parent. Okay, so now when you fill out your Punnett square, right, you get H plus 25% of the time, 1/4 out of this box. You get H plus HS, 2 out of the 4 boxes, so 1/2 the time you get a heterozygote. And then 1/4 of the time, you get a homozygous recessive individual where they got an HS from both parents. Okay? So the genotypic ratio, that is what we were talking about there, is 1 to 2 to 1. So 1/4 of the individuals are homozygous dominant. 1/2 of the individuals are heterozygous, and 1/4 of the individuals are homozygous recessive. But most of the time we're actually interested in the phenotype, which is what you see, right? So these heterozygous individuals will look exactly the same as the homozygous dominant individuals, because that is the definition of dominance, right? The heterozygote shows the dominant trait. So we have 3/4 of these individuals, 3 squares out of the 4, will have curly hair, and 1/4 of the individuals will have straight hair. So we have these two different, you have 1/4 plus 1/2 equals 3/4, and then you have 1/4 plus nothing equaling 1/4. So this is the ratios that you get for the monohybrid cross. Okay. So that's your expected value. Sometimes when you do like trials, right, you'll get something a little off, and that's why we use this as our null hypothesis for like these ratios, the 3/4 and the 1/4, as our null hypothesis for what ratios we should be getting if Mendelian genetics is happening correctly. So what you're going to want to do is, like, you know, if you get like 100 individuals, right, you're going to expect 3/4 of them, or 75 of them, to have curly hair, and then you're going to expect 1/4 of them, or 25 of them, to have straight hair, and then you're going to compare that to what you actually see, which might be like, you know, like 80 and 20, and you see if that still seems significant, if the chi-squared value puts you in a position where you still are getting a p-value for that number of degrees of freedom. This would be 1 degree of freedom. That, like, it's still above 0.05 p-value, and that would mean that you accept the null hypothesis. And our null hypothesis here is that we're doing a monohybrid cross with these traits.